Oakley dokley. Okay, so no issues out the jump, which leads me to believe there will be no issues. Yep, all right, we're moving, no problem. Cool. Local rotation. Let's do it.
Hello and welcome back. Now we are moving our tank forward and backward, but we have no way to actually steer the tank. So in this video, we're going to work on actually turning the tank using something called local rotation. This is the rotational analog to add actor local offset. Now add actor local offset had multiple input parameters, and we only passed in the first one as the other three were optional. But one of those other three had to do with sweeping, and we're going to discuss a little bit about sweeping before we continue implementing rotation. So I'm back in the documentation for add actor local offset. So let's take a look at these input parameters once more. The second one is called bsweep, and it's a Boolean. Now, if we scroll down a little bit more and read the information here for bsweep, it says whether we sweep to the destination location, triggering overlaps along the way and stopping short of the target if blocked by something. It also goes on to say that only the root component is swept and checked for blocking collision. Child components move without sweeping. If collision is off, this has no effect. So let's talk about what this means. Now, in games programming, sweeping is a technique done by the engine as long as sweeping is enabled. If we have a moving object, such as a sphere represented by this circle, each frame, as this sphere is moving, the engine is performing sweep checks. This means it's checking to see if that move for this particular frame would have resulted in an overlap between two objects. So I have this block here represented by this rectangle. Now let's just consider that these are the only two objects in the world. So while sweeping is enabled, as the sphere is moving towards the object, the engine is checking to see if these two objects are overlapping. Now as the sphere continues to move, let's say during one of these frames, the sphere would have moved such that it's overlapping the other object. Now, what sweeping enabled does is the engine will detect this overlap and move that sphere back for that particular frame so that it never actually penetrates the object. Now, we never actually see the sphere penetrate the object. The engine catches that overlap before the movement is actually implemented, so the result is that we see that the sphere stops just short of overlapping. So if this rectangle were a wall, for example, the sphere would stop at the surface of the wall. That is what sweeping achieves for us. Now, the documentation says if collision is off, this has no effect. So collision has to be enabled in order for sweeping to work. So back here in tank.cpp in the move function, here's our call to add actor local offset. And if we want, we can pass in another input parameter here, the second one being the sweep boolean. So we can pass in true here. So let's compile this and see the effect of enabling sweeping. Now, if we press
Weather looking like today. Weather. Live coding.
play and we attempt to move through a wall, for example, we'll see that we move right through the wall. So something isn't quite working here. Now let's look at what that root component for the BP pawn
Oh, I moved through it.
tank is. Recall we used the capsule component for the root. So with capsule component selected in BP Pond Tank, let's go to the details panel and scroll down, and we'll see here a section called collision. And here we see collision presets. And it has a drop down, so let's expand that. Now collision
Collision.
presets can be set to any number of options, and by default we see overlap all dynamic. Now depending on the version of Unreal Engine you're using, you may see something else here, but we can change this. If we select the drop-down and choose block all dynamic, then the grayed out options below change. Remember, we were on overlap all dynamic, and here we see 3 columns of checkboxes. These are collision responses, and the column to the left show a list of collision object types. So any given component has its own collision object type. Notice we can see the object type for the capsule set to world dynamic. And when we changed collision presets to block all dynamic, you'll see that the collision responses are all checked to block in response to all other collision object types. So let's press play and see what happens when we try to pass through things. You'll see that we stop just short.
Can't move now? Why can't I move?
Of overlap.
That's weird.
Overlapping with the other pawns. Now, if I move the tank so that we can attempt to overlap with the wall and sort of go around the other pawns, now if I press play, I block the wall as well. So this collision preset.
Okay, so I'm getting an error that they are not. It's AI controller.
something else here, but we can change this. If we select the dropdown and choose Block All Dynamic, then the grayed out options below change.
Oh, shoot. All right. Okay. This is causing them. Cool.
Remember, we were on Overlap All Dynamic, and here we see 3 columns of checkboxes. These are collision responses, and the column to the left show a list of collision object types. So any given component has its own collision object type. Notice we can see the object type for the capsule set to World Dynamic. And when we changed collision presets to Block All Dynamic, you'll see that the collision responses are all checked to block in response to all other collision object types. So let's press play and see what happens when we try to pass through things. You'll see that we stop just short of overlapping with the other pawns. Now, if I move the tank so that we can attempt to overlap with the wall and sort of go around the other pawns, now if I press play, I block the wall as well. So this collision preset, Block All Dynamic, sets the collision response to block all other object types. And you can always see the collision object type of a particular component by selecting it in the Components panel and scrolling down to the collision section in the Details panel and opening the dropdown for collision presets. I have the base mesh selected, and its object type is World Dynamic, and it's set to block all. So now we see that sweeping is working since we set our collision presets for the capsule comp to block all dynamic. And we saw in the documentation that only the root component is swept and checked for blocking collision. So it doesn't really matter what the other components are set to. We're only checking to see if the root component is blocking something. Now, one issue that's tripped up some students is that they cannot move as soon as they set the capsule to block all dynamic. Now, one reason for this could be that your capsule is overlapping with the floor. If the capsule is overlapping with the floor, you won't be able to move because the engine will not allow your tank to move if the capsule component is overlapping with something that it's set to block. So an easy fix for this would be to make sure your capsule is not overlapping with the floor. Now you can go into your BP Pond tank and make sure that your capsule is just above the wheels here. I'm going to go into orthographic view and select my base mesh and just bring it down so the wheels are just below the capsule component. So now if you're
Duh, that's what I was doing. Oh, we'll do it all. Before. Orthographic. Can I change this to... There we go. Ah. Undo snap. Where is the snap? Now we're moving. That was the issue.
mesh is just on the floor and the capsule is just above the mesh, you should be able to move around. So I'm going to hit play, and there we go. So now that we have sweeping out of the way, it's time to start implementing rotation. Let's go back to our project settings. So we go to Edit, Project Settings, scroll down to Input, and in the Input section, we have our axis mappings. Now we've already taken care of Move Forward. Project Settings, scroll down to Input, and in the Input section, we have our axis mappings. Now we've already taken care of Move Forward. It's time to take care of the next one called Turn. And Turn has D and A assigned to it, where D has a scale of 1 and A has a scale of -1. We'd like to use the D and A keys to rotate the tank. So in order to bind a function to the turn axis mapping, we need a function to bind. So we're back in VS Code, and I'm going to go into the tank.h file so we can create a function to bind to that turn axis mapping. Now I'm just going to call this void function turn, and just like move, it needs a float input parameter, and we'll call this value. So we've declared this function. Let's define it in tank.cpp, and I'm going to put it just under the move function. So I've given it a function body, and I need the class name along with the double colons just before the function name. Now we have a proper function. Now this isn't the only thing we need to do. We need to make sure that this function is bound to the axis mapping called turn. We do that in setup player input component, and we do it just like we did the move forward axis mapping. So we're going to say player input component. We're going to use the arrow operator and bind axis. Now, the first parameter is going to be the axis mapping name wrapped in a text macro. So we're going to say turn, as that was the axis mapping name. Next is the object we're binding the function for. We can pass in this. And finally, we pass in the function we'd like to bind. Again, we need the address of operator, and it's going to be a tank turn. So it's as easy as that. We've bound the turn function to the turn axis mapping. The only thing left is to...
This is bound to... Gotcha.
Actually do something in the turn function. Now we've seen that we have add actor local offset, but there's a rotational analog to this function, and it's called add actor local rotation. What this does is adds a local rotation to the actor, as its name suggests. And you'll see that there are two different versions of the function, one that takes an F rotator and one that takes something called an F quad. We're going to use the version that takes an F rotator. It's called delta rotation, and just like add actor local offset, it can also take a sweep parameter and the same other 2 input parameters as add actor local offset, and these last 3 input parameters are optional just like add actor local offset. So instead of an f vector, we're going to pass in an f rotator. Now back here in the turn function, if we create an f rotator, and we call this delta rotation, we'll see that if we right-click on f rotator and go to definition, we're taken to rotator.h, and we'll see 3 public.
You declare this an H? No, you turn.
This delta rotation, we'll see that if we right-click on f rotator and go to definition, we're taken to rotator.h, and we'll see 3 public member variables here of type float. Now, just like the f vector, f rotator.
You're looking at something different. You're looking at a struct. In math? No, you're in rotator.h. F rotator. Pitch, yaw, and roll.
Has these 3 components, only instead of x, y, and z, we have pitch, yaw, and roll. Now, yaw is the component that we're interested in. It says rotation around the up axis, in parentheses, around z axis, and that's the only type of rotation we care about, rotating around the z axis. That's how we can steer our tank. Now, I'm just going to point out to you that there are multiple constructors for the f rotator as well, and that the default, again, says no initialization, just like with the f vector. So we can use the one that takes a single float, and all components will be initialized to that float value. There's one with 3 float values, and you can take a look and see some of the others. Now, I'll also point out that there's a 0 rotator. And by the way, this is a static 0 rotator. That's why we can go back into tank.cpp and say something like equals f rotator 0 rotator. 0 rotator is a static member variable, and you can access static member functions and variables like this by specifying the class name with the scope resolution operator and referencing that static variable or function by name. That's what we're doing here with uGameplay statics. GetWorldDeltaSeconds is a static function, meaning we don't need an actual instance of the uGameplay statics class to exist for us to access that static function. It just exists already. Same with 0 rotator and 0 vector. So I'm going to close out of rotator.h, and we have this delta rotation, and it's initialized to a 0 rotator. Now, yaw, pitch, and roll are zeroed out, just like x, y, and z are zeroed out for the f vector. So we're going to need to change that yaw component. So just like I did with our delta location in the move function, let's create some pseudocode for delta rotations yaw. We're going to want yaw to be set to value, scaled by delta time, of course, because we want this turning to be frame rate independent, but we also need some sort of turning speed. We can call this turn rate. So once we've set that yaw, then we can add that local rotation, which is going to rotate the actor according to the f rotator each frame, and that yaw will be scaled by value. So it'll be 0 if we're not pressing any keys, and it will have a value if we're pressing the D and A keys. So now you have a challenge. This is going to work just like adding the actor local offset. The only difference is we're rotating the actor now. So since we need some sort of turn rate for rotating the actor, you're going to create a turn rate variable. Make this a float and put it in the private section right next to the speed variable. Expose this variable with uProperty and choose the appropriate uProperty specifier.
Need a turn rate.
Now in the turn function, you're going to set delta rotation. In particular, we care about the yaw component. Set the yaw value equal to value times our turn rate variable and also multiply by delta time. And then you're ready to call add actor local rotation, passing in this f rotator. Now for the second parameter, go ahead and pass in true for the B sweep input, since we do want to sweep when rotating. Pause the video and implement rotation for the tank now.
Pause the video now. This will be delta rotation dot y, I think it is, equals, or is it dot yaw? Value times delta. Well, it'll be u game play statics get world delta seconds this times turn rate, and then tank.h we can make a private video. I don't know. Live code to Bish. Oh man, is this gonna compile first try? This would be sick. Oh, okay.
Okay, so this is going to be fairly simple. We just need a turn rate variable. Now I'm going to go into tank.h just under speed and create float turn rate. You probably initialize this to some value, and that's okay if it's different than what I'm choosing. I'm going to go with 45.f and see how that works, but we're going to expose this to blueprints so we can change it while we're developing. Now, I'd like it to be edit anywhere, and I'm going to stick it in the same category movement as speed. So I'm going to go ahead and steal this U property and paste it right here above turn rate, so it's edit anywhere, category movement. Now in tank.cpp, I'm ready to set the yaw for delta rotation. So we're going to say delta rotation.yaw, and we're going to set it equal to value times turn rate times delta time. And of course we can get delta time with u gameplay statics get world delta seconds, passing in this as the world context object. So I'm going to paste that right there. Now, I know that my pseudocode doesn't exactly match. It's in the wrong order. Delta time is in the middle here. It doesn't matter because when multiplying three values together, you can multiply them in any order and still get the same result. So just in case you were wondering about that, the math will still come out the same if you multiply these three values in a different order. So don't worry about that too much. Now we have delta rotation. The only thing left to do is to call add actor local rotation. And we're passing in delta rotation, and for the second input, we're going to pass in true to enable sweeping when rotating. So let's compile this. All right, we're compiled. Now you may notice in a couple of the next videos that zero vector and zero rotator are missing from these lines. That's because I started off with these uninitialized and realized later that these should probably be initialized, at least with the zero values. So don't worry if you see these lines later looking like this, uninitialized. Keep your zero vector and your zero rotator, and you'll see that I catch this in a near future video, so don't worry if you don't see these initializations, they should be there. And we're back in the editor, let's hit play, and I'm going to use the D key, and we're rotating, and
Oh, we're moving, baby.
the A key rotates me back the other way, and we can also move forward and back. So now that we can rotate and move forward, we have the ability to move around the world. This is a great milestone. Now I'm moving quite slowly, but that's okay because I can select my tank and I can search for the movement category and change turn rate to something higher, such as 90. So let's go ahead and hit play. And that's quite a bit faster. Now, if you think this is still a little slow, you can, of course, adjust these. So I'm going to select the pawn tank again, and instead of 400, let's make it 800. Why not? And instead of 90, let's go to, say, 120. Now, if I press play, I'm quite a bit faster. So this is looking really, really good. So looking back at the section plan, we now have a tank that can move throughout the world. That first bullet point is definitely checked off. And we're handling WASD movement. We're not handling mouse input just yet, but we'll get to that. But we're one step closer to making this game complete. So in summary, we learned what sweeping is and how we can enable that so that our objects do not pass through one another. We added an actor local rotation, and we did this implementing a turn rate that we could adjust in the details panel in the editor to make development a little bit easier. Great job. We're now moving the tank. Hello and welcome back. Now we have movement for the pawn, but we're not rotating that top part of the pawn, which we're calling the turret. So we'd like to be able to do that using our mouse. Now take a look at what's going on here. As I'm moving my mouse cursor around in the world, I'm getting this red sphere. This is a debug sphere that I'm drawing in 3D space. Now notice as I move up against a wall, that sphere moves against the surface of the wall. So wherever my mouse cursor is moving, I'm getting this sphere that corresponds to whatever object I'm hitting based on my cursor location. And this is going to be useful for us so we can have a location in space that we can rotate our turret towards. Now, in order to do this, there are some functions we need on the controller. So we have to access those functions on the controller, and in this video, we're going to work on setting that up. And we're also going to discuss how this is going to involve a concept known as casting. Now, the reason we want the controller is because there are functions on the controller that allow us to get the hit result under the cursor. Now, we're talking about the mouse cursor. So say this is our screen, and here's our mouse cursor. And the point at the tip of the cursor corresponds to a location
No!
on the screen. Now, if we move the cursor around, our goal is that the turret part of our tank, that top part of our mesh, is going to rotate so that it's facing the direction of that cursor. Now, if we move the cursor around, there's a function on the controller that we can use to get the location corresponding to that cursor. If we were to draw a line straight out from the camera towards the cursor and hit some object in the world, we can get that location and use that location to set the rotation for the tank turret. Let me show you what I mean. Now, in order to get this hit location corresponding to our cursor, we need to use the controller. Now, let's talk about the controller for a brief moment. Let's say we have our pawn in the world. A pawn will have a controller. This is an invisible object that's associated with the pawn. Now, for our pawn, our controller is going to have the type A player controller. And at the beginning of the game, the controller will possess the pawn. This is why we can see from the point of view of the camera that belongs to our pawn tank. Now we can access this controller. Our tank class inherits a function called getController. It's inherited from the pawn class. So what we'd like to do is get a hold of that controller and store that in a variable so that we can use it to access the function we need to get the hit result under the cursor. So let's set ourselves up for that. Now I'm here in the tank class, and the place we need to access our controller is begin play. If we do it in the constructor, that's too early, and we may not have a valid controller just yet. So we're going to need the begin play function here in the tank class. Now we have it here in the base pawn class, and so far we're not really using begin play in the base pawn class. So what I'd like to do is move it over to the tank class. So I'm going to highlight begin play, including the comment and the protected section here, and I'm simply going to cut it, and then back in tank.h.
Wait, I missed that. I was spaced out.
And here in the tank class. Now we have it here, and the place we need to access our controller is begin play. If we do it in the constructor, that's too early, and we may not have a valid controller just yet. So we're going to need the begin play function here in the tank class. Now we have it here in the base pawn class, and so far we're not really using begin play in the base pawn class. So what I'd like to do is move it over to the tank class. So I'm going to highlight begin play, including the comment and the protected section here, and I'm simply going to cut it. And then back in tank.h, I'm going to paste it. Let's add this protected section here just above the private section with begin play inside. Now we've removed begin play from base pawn.h. We no longer have it here, but we also need to remove it from base pawn.cpp. Here it is. We can go ahead and delete it here. And now we have it declared here in tank.h, but we also need to define it in tank.cpp. So I'm going to define the function just under setup player input component. So it's going to be void begin play with no input parameters. There's the function body, and we also
Yeah. A tank.
Prefixing the function name. Now we know it's important to call super begin play, so that way any functionality in the begin play function in any of the parent classes will be still called. So here we have begin play. This is where we can get our controller and store it in a variable. So let's go back to tank.h and create a variable. Now this is going to be private, and I'm going to stick it down here at the bottom of the private section, and it's going to be a player controller pointer type. And we can call this player controller ref. This will be our reference to the player controller. Now we're not talking about a C++ reference. This is still just a pointer, but we're going to use this to refer to the player controller. So now we have a player controller ref variable of type A player controller, and we're ready to store the controller in this pointer. So let's go back to tank.cpp here in begin play and attempt to do this. So what I'm going to do is say player controller ref equals, and I'm going to attempt to call get controller. Now get controller, as I mentioned, is on the pawn class. Let's right click and go to definition, and notice that this function returns an A controller. Now, our variable is of type A player controller, not A controller. So what we're attempting to do.
This is actually returning a UI K-rig controller. Uh-oh.
Here, that this function returns an A controller. Now, our variable is of type A player controller, not A controller. So what we're attempting to do here is take the return value from get controller, which is of A controller pointer type, and we're trying to store it in an A player controller pointer. Notice we see the red squiggly here. It says a value of type A.
That's a follow. David John, what up, homie?
Controller pointer cannot be assigned to an entity of type A player controller. We're getting an error. Let's take a look here at the documentation for A controller. Take a look. Here's A controller, and it says inheritance hierarchy. And below A controller, we see a AI controller and a player controller. This means...
Bruh. What?
A player controller is a child class of a controller. Now in C++, we cannot have a pointer of type a player controller store the value of the address of an a controller. A controller is the parent type, a player controller is the child type. You cannot take an object of parent type and store it in a pointer of child type. So how do we get around this? So here's our problem. The getController function returns the address of an a controller. Now this is something we could store in an a controller pointer, but we can't store it in an a player controller pointer. The funny thing is though, that the object returned by getController is in fact a player controller. So we have this address in the form of an a controller pointer, and we know it stores a player controller, but if we have it in the form of an a controller, we cannot access the function that we need because it exists on a player controller. The function is called getHitResult under cursor. Now if we have a value of type a controller pointer, and we attempt to get that function that exists on a player controller, we will fail to do so. We'll get a compilation error. So since we know the object itself...
What up, David John? David. I'm doing well, bro. How are you? Doing some game development right now.
Is a player controller. It's just stored in an a controller pointer. How do we get around this problem? The answer is we have to cast. We know that a controller is the parent class and a player controller is the child class. And we know that we cannot have an a controller stored in an a player controller pointer. We know we can go the other way around and have an a controller pointer store an object of a player controller. That's in fact
What about you? I'm developing some games.
what we're seeing when we call getController. It returns an a controller pointer that points to an a player controller. So if we have a value of type a controller pointer,
Just cast
there's a
it.
special function called a cast to convert the type of the pointer to an a player controller pointer. So casting changes the type of one pointer to another pointer type, as long as the object itself is the type that we're trying to cast to. Now if we attempted to cast to an invalid type, for example we have an a controller pointer pointing to a player controller object, if we attempt to cast to, say, a character, the cast function returns null, and we say that we fail the cast. So the cast function looks like this. It's a template, just like create default subobject. This template function will adapt to the type chosen, and in this function, the type we pass in is the type we're casting to. So we pass that type we'd like to cast to inside the angle brackets, and we pass the pointer that we'd like to cast into the parentheses. Here's an example. Let's say we'd like to cast to a player controller in a pointer of type a controller type. We pass the pointer into the parentheses and the type we're casting to in the angle brackets, and what gets returned is a value of type a player controller pointer. So here's the function call where we're passing the type in the angle brackets, and the a controller pointer value that we get returned from getController can go in the parentheses. So we need to cast this value that we're getting returned from getController. That's going to be your challenge. So in begin play, use the getController function and pass that value in to the cast function and cast to a player controller. And then you can store the result in our player controller ref pointer, which is
I'm from
type A
Chicago.
player controller pointer. Pause the video and perform the cast.
Where are you from?
Okay, so we've almost got all the work done here. We just need to cast. So what we're going to do is call the cast function, which has angle brackets as well as parentheses. And what goes in the parentheses is the value that we'd like to cast. Now, getController returns a pointer of type a controller. I'm going to move that right here into the parentheses, and the type we're casting to is a player controller. So again, we're taking the value returned by getController. This returns an a controller pointer, or an address. Then we're using cast to cast it to an a player controller. We know that the object returned by getController is an a player controller object stored in an a controller pointer. So after we've cast this, what gets returned is a pointer of type a player controller. So we're storing that in player controller ref. Now that we have access to the controller in the form of an a player controller pointer, we can access the function we need to get the trace hit result under the cursor. So in summary, we used getController to gain access to the controller. We also use the cast function to cast from the type a controller pointer.
Nice to meet you.
Controller pointer. Now we can access the function we need.
Hell yeah, bro. What time is it in the UK right now?
On the a player controller class. So we'll start using this function. In the next video. I'll see you soon. Hey, welcome back. Now, we know that we need to get the hit result under the cursor. We're going to talk a little bit more about how that works.
No, I'm just doing it
in this video. So our goal is to get the hit result under the cursor and show
this I'm just doing it.
And we can do so by drawing.
What time is it where you are?
We'll learn how to do that as well. So let's talk about something called a hit result. In games, we'll often want to do something like this. We'll have a point in space. We'll call this point start, and it has the type f vector. And we'll have an end location. This will also be a point in space of type f vector. Now let's say we'd like to draw an invisible line from the start point to the end point. And at the moment we draw this line, we'd like to see if there are any objects in between the start and end locations. Now if there are, then this line that we're drawing in space is going to hit that object on the surface. When this happens, we call this a hit event. Now when we draw an invisible line like this, it's called performing a line trace. And when we hit something, we say that we have a trace hit. Now if we do hit something and get a hit event, then the trace hit stores information in a struct called a hit result. Its type is fHitResult. Now the fHitResult struct contains variables that store information about the hit event, including the hit location as an f vector in space and the actor that we hit, among other information. Now when we perform a line trace, we do so by specifying a collision channel. Usually with line traces, we choose the channel called visibility. There exists an enum called eCollision channel, and in this enum, there's an enum constant called ECC visibility. This is one of the parameters we specify when performing a line trace. Now, if we specify the visibility channel, that means objects that are set to block the visibility channel in their collision settings will register hit events. Any objects that are not set to block the visibility channel will not generate hit events. Now, we would like the trace result under the cursor. Imagine we have the screen here, and here's our cursor. Now, at the tip of our cursor, we have a point on the screen. When we use the function to get the hit result under the cursor, what happens is we have our camera, and it may see some objects in the world, such as the floor here, and we're performing a line trace from the camera at the point on the screen corresponding to our cursor location, and we're shooting the line trace straight out into the world. And if we hit something, we'll generate a hit event and store the information in a hit result struct. So let's find out how we can do this. I'm here in tank.cpp, and what I'd like to do is get the hit result under the cursor every frame, which means we need the tick function. So again, we're going back into basepawn and finding our tick function here. Now we're not using it for anything in basepawn, so we can move this function into the tank class, just like we did with begin play. So I'm going to highlight the function declaration along with its comment and copy it. And after that, I'll delete this whole section, public and all. And then I'll go back into tank.h, and here in the public section, I'm going to paste the tick function declaration. Now we're not using it in basepawn, so I'm going to remove the tick function from basepawn.cpp. Now it's gone from basepawn. Now we have it here declared in tank.h, but we also need to define the function in tank. .cpp. I'm going to do it here in tank.cpp just under setup player input component. So we're going to say void tick. It takes a float called delta time, and there's our body. Now again, we need a tank just before the tick function along with the scope resolution operator. And we also need to call super tick and pass in delta time. So we now have tick on the tank class. What we want to do is get the hit result under the cursor. So here's how we do it. The function we're going to use exists on the player controller called getHitResult under cursor. We've been talking about this. Now here's the syntax. It takes a trace channel. Remember, we need to specify a trace channel, and we're going to use visibility. Now we have two additional input parameters. The first is a bool called bTraceComplex. We'll talk about what that means in a second. And the third input parameter is an fHitResult. Now I'm going to click on fHitResult just to see this type here in the documentation. And if I scroll down, we'll see some the variables. One of them is called actor, and its description says actor hit by the trace. We also have this B blocking hit, which says indicates if this hit was a result of a blocking collision. Now, among the other variables, we have things like impact point. This is the location in space where we actually hit something. So why don't we go ahead and attempt to call this function? We first want our player controller, and thanks to what we did here in begin play, we have player controller ref. Now the first thing we should do is check to see if player controller ref is valid. We can always pass a pointer into an if statement. It'll return true if the pointer itself is not a null pointer. If it is a null pointer, it'll return false in an if statement, and will never reach the inside of the if statement. It's always a good idea to check our pointers and make sure they're not null before we use them. Now we're going to get our player controller ref, and we're going to use the arrow operator to call the function getHitResult under cursor. Now we can see with the pop-up that we have three input parameters. The first is the trace channel. We're going to use eCollision channel, and if we type 2 colons, we get a dropdown that shows us all of the different enum constants in the eCollision channel enum. We want to use visibility, so we're going to type ECC visibility to specify that we're using the visibility channel. Now the next parameter is called bTraceComplex, and we're going to pass false into this. Now we'll discuss in a few minutes what this means, but for now we're going to use false. Now for the third parameter, we need a hit result. This is a struct of type fHitResult. Now if you hover over this, you'll see that fHitResult is being passed in as a reference, as indicated by the reference operator that looks like an ampersand. Now, usually when you pass something in as a reference, it's a const reference, meaning the function won't be able to change it. But here we're passing in an f hit result as a non-const reference. This is generally a hint that the function is designed to change this input parameter directly. What getHitResult under cursor is going to do is fill in those variables in the f hit result with information about the hit result. This means we need to pass one of these f hit results in. We're going to create a local variable here in the if check of type f hit result, and we can call this hit result. And we can simply pass this in as the third input parameter. Now, after we've called this function, then this hit result will be filled in with data about this line trace. For example, we can access hit result dot actor to get the actor that was hit, or dot impact point to get the point in space where we had the hit event. So the hit result is what we will use to get information about the line trace. Now, often it's nice to be able to see the result of a line trace. We can easily visualize the result of a line trace by drawing a debug sphere. Debug spheres are simple shapes that we draw in space, and they're great for showing a location, and we use these when debugging. We don't actually use debug spheres in a shipped game. So let's see how we can draw one of these debug spheres. Now here's the documentation for a function called drawDebugSphere. It exists in drawDebugHelpers.h. So we can copy this header and include it wherever we'd like to call drawDebugSphere. Now look at all the input parameters. First, it takes a world. This way it knows which world to draw the sphere in. It takes an f vector for the center of the sphere, as well as a float for the radius. It takes an int32 for the number of segments for that sphere. The more segments, the more round the sphere. It takes an f color. This way it knows which color to draw this sphere in. It wants to know if you want persistent lines. In other words, should the lines disappear immediately or should they persist? If they do persist, it wants to know the lifetime of the sphere. When should it stop drawing the sphere? If you don't draw persistent lines, say you'd like to draw it for a single frame, then you would pass -1 in as the lifetime. Now the last two parameters are optional, so we'll keep this simple by only discussing the first 7 parameters. Let's see how this works. I'm going to draw a debug sphere. Now up at the top, I'm going to include drawDebugHelpers.h. That's where this drawDebugSphere function is declared. Now let's go down to begin play and just simply draw a debug sphere to see how this works. So I'm going to call drawDebugSphere. And the first input parameter is a uWorld. We can get our world at any time by calling getWorld. GetWorld returns a uWorld pointer to our current world. So that will satisfy the first input. Next, we need an f vector for the center of the sphere. Now we're calling this in begin play. So I can simply call getActorLocation. And this will get the location of our tank pawn since we're in the tank class. Now I'm going to raise the sphere up by a bit. So I'm going to add an f vector with 0.f for the x, 0.f for the y, and say 200.f for the z. Now I'm going to place these input parameters each on their own line so it's clear what we're passing in for each input. The second input is getting this expression, which is the actor location plus a vector pointing upward with a length of 200. Adding these two vectors together will give me the location of the tank raised up in the z-axis by 200 units. Now the next input parameter. It's going to be the radius of the sphere. I'm going to choose 100.f, just so we can see what a debug sphere with a radius of 100 looks like. Next is the number of segments. I'm going to choose 12. We'll see what that looks like. Now for an f color, there exists an f color class, and it has lots of colors built in, such as red. Now for the boolean called bPersistentLines, I'm going to choose true. And for the next input parameter, we have the lifetime. Notice it has a default value of -1. That means by default, it'll draw the debug sphere for a single frame. But I'm going to pass in 30.f so that we get the sphere for 30 seconds. And I can omit the last 2 parameters. So here's our function call to draw debug sphere. Let's compile this and see what it looks like. Okay, so I'm back in the editor. I'm going to open a second window so we can see So here's our function call to draw debug sphere. Let's compile this and see what it looks like. Okay, so I'm back in the editor. I'm going to open a second window so we can see this in full screen. I can go to Window, Viewports, and select Viewport 2. And now I see this second window. It may not be full screened when it opens up, but you can always maximize it. Now from
Crash report. Uh-oh. Probably because of Nikes. Did that save? Compile. Okay. We're live coding this. So, aha. Viewport 2 crashes my freaking... Why do you want to open a second viewport here? What are we doing?
Here I can play the game with Alt-P. Now check this out. Here's our debug sphere. Notice it's not perfectly round. We chose 12 for the number of segments. The more segments you choose, the more lines it takes to draw the sphere. Now this is a sphere with a radius of 100. It's pretty big. And the center of the sphere is at the location of the tank plus 200 units up in the air. So this is how we can draw debug spheres. So your challenge is to draw a debug sphere using the trace result under our cursor. So draw a debug sphere in our new if statement where we're checking if player controller ref is not null. Now, using our hit result, get the impact point from the hit result and use that as the center for the sphere. Now, for the persistent lines input parameter, use false, and for the duration, use -1. And this will result in drawing the sphere for a single frame, which is okay because we're calling this every frame inside the tick function. So pause the video and draw the debug sphere in the tick function. Okay, so I'm back here in tank.cpp. Now I have this draw debug sphere function call here in begin play. So I can go ahead and copy that and just remove it from begin play. And we're going to go back up into tick here inside of our if statement. And I'm just going to paste it here. And we're going to change some of the input parameters. For one, we're changing the location for the center of the sphere. We're going to use the hit result. So I'm going to say hit result dot impact point. Now for the radius, I'd like to make this a bit smaller. Let's make it about 25. That's okay if you didn't do that. I'm just doing this so the sphere is not so big. Now, the second to last parameter we're passing in is for persistent lines. I'm going to pass in false, and for the duration, instead of 30 seconds, I'm going to use -1.f. That way, we'll get a sphere for a single frame, which is okay. Again, we're calling this in the tick function, so we'll be calling this every frame. Let's go ahead and compile this. Now, back in the editor, if I hit play, now check this out. I have a debug sphere, and it's being drawn at the impact point for the line trace under the cursor. Now we can move this up the walls and on other objects, and the trace is hitting these objects because they're set to block the visibility channel. Pretty awesome, right? Now, I promised we would discuss tracing complex versus tracing simple. I'm going to show you something. While we're playing the game, let's click in the viewport so that we have control over our pawn. Now hit the tilde key and type the console command show collision. Now, it may not be so easy to see on my screen, but you can definitely see it on your screen. Notice the collision for our pawns. Not only can we see the capsule, but we can see this collision volume around our tank and turret meshes. This is simple collision. Let me just show you real quick where we can see the simple collision. I'm going to go into Assets and Meshes, and if I double click on, say, Tank Base, here we're looking at the complex collision. If I click on this show icon here at the top and select complex collision, I can see all of the polygons in the complex collision, and there are a lot of them. If I click the show icon again, and this time check the checkbox next to simple collision, notice there's another collision volume. This is called a collision hull, and it has a great deal less geometry. There is a smaller number of polygons with this collision volume. This is what the physics engine uses to detect for overlap and hit events. If it were using the complex collision, it would require a great deal more computations. This is why we have simple collision volumes. So it's much better for performance whenever doing a line trace if we trace for simple collision instead of complex collision. So now we've gotten the hit result under the cursor. It took some work to get there, but now we have it, and we've proved it by showing this location with a debug sphere. This is a nice way to confirm that our trace hit is working. So now that we know it's working, we can use that location to rotate the turret on our tank. And we'll do that in the next video. I'll see you soon.
Okay, I'm gonna stop here for now. Seems like a good spot. Control S, we just compiled, so should be all good. And let's go to Minecraft.